1954, when germanium was the world's first choice as a basic semiconductor material, scientists at the Wythenshawe laboratories decided that Ferranti's development program would be based upon silicon as the material most likely to satisfy equipment designers' requirements in the future. During the next 7 years, a wealth of knowledge was gained, and Ferranti produced for the first time in Britain such devices as conductivity-modulated diodes, diffused power rectifiers, and Mesa and planar transistors. This work laid a foundation of skill and discipline on which has been based the production of the most significant electronic component since the thermionic valve, the integrated circuit. And it won for the Ferranti Electronics Department a position of superiority which cannot be challenged by any dependent operator, functioning merely as the tail end of a production line, controlled by some organization far removed in distance, time, and loyalty from the United Kingdom equipment maker. The integrated circuit, even at its present level of development, can improve the cost versus computing capability factor of a computer by more than 30 times compared with the best that can be done with discrete components. By no means satisfied with this, Ferranti engineers continually seek, aided by customer design teams, methods by which British electronic equipment can be made even more competitive in world markets. In a typical case, study of a customer's machine logic diagrams resulted in a choice of circuit configuration by which the relationship between speed and power dissipation was improved by a factor of 5 over the conventional off-the-shelf integrated circuit, and requirements in silicon chip area were reduced by 50%. The whole story of Ferranti semiconductor manufacture is characterized by similar original thinking and recourse to first principles. Theoretical design, which may be computer-aided, is often followed by practical experiment, in which the proposed circuit is simulated by a mixture of integrated and discrete components to enable its performance to be evaluated. With the knowledge so obtained, the circuit design can be finalized, and the Ferranti engineers then go on to translate it into terms of a standard range of integrated components and diffusion schedules. This results in a layout with no obvious resemblance to the original circuit, but containing all the information necessary for the preparation of photographic masks which will control the subsequent processing of the silicon. This elaborate key diagram is 1,000 times larger than the final integrated circuit. There may be as many as 12 or 15 masks in all for one type of circuit, and the layout of each is derived from the master drawing. Using the layout as a guide, but remeasuring dimensions as she works to ensure accuracy, this operator marks off and removes parts of the colored layer of this laminated material, the resulting pattern defining which parts of the silicon will be protected and which exposed to chemical action in each particular process. A set of transparencies on a smaller scale shows the complex interlacing of the circuit elements defined by a typical set of masks. Only 6 are shown here. Sometimes there are many more. The standard of precision maintained throughout is such that lines as narrow as a 10,000th of an inch are possible in the final circuit. Photography in various specialized forms is prominent in microcircuit manufacture from this point on. In the first of a series of darkroom operations, each mask design is photographed to produce a negative image 1/10 of the size of the original. The negative from the first camera is then photographed, again reduced 10 times, so that a picture of the mask 1/100th of the size of the original is obtained. Each mask of the set gets the same treatment. The mask has now been reduced to 1/100th of its original size. A highly specialized step and repeat camera, electronically controlled, performs the final reduction. It is designed to make at one time not one but a complete set of up to 16 different masks for one microcircuit. It is in effect 16 cameras, all working in unison. The plates on which the copies are being made are set in a carriage which moves continuously in a back and forth scanning pattern. Electronic flashes at set intervals make the exposures. The result is that each plate this size, photographed by this camera, is reduced to a 10 times smaller image repeated many times, and a set of masks for the circuit is completed in one operation. Silicon crystals, thick bars up to 1.5 inches in diameter, are sawn into hundreds of thin slices. The slice form persists through all the operations which follow until processing is almost complete. The slices are polished in metallurgical polishing machines using alumina or diamond paste to a mirror finish. Those intended for microcircuit use, the silicon is differently doped for different purposes, are treated in furnaces in which a very thin epitaxial layer of doped silicon of a different type is deposited on them. The slices lie in a quartz tube surrounded by a radio frequency heating coil. Hydrogen and silicon tetrachloride vapor doped with phosphorus passing over the slices builds up the epitaxial layer. The process is almost entirely automatic. In another furnace treatment, the surface is then uniformly oxidized by heating in a moist atmosphere. The colors seen on oxidized slices are due simply to the thinness of the oxide coating. This is the beginning of a long series of processes designed to create in the material the junctions which will form the transistors, diodes, resistors, and other components of the integrated circuit. All these operations are carried out in conditions of extreme cleanliness. In this room, there is provision for printing the various masks photographically onto the silicon slices and for developing the images so produced. The first step is to pour a few drops of a special photographic emulsion onto each slice and to spread it evenly by spinning. After this, the first mask is placed in contact with the slice and an exposure made under ultraviolet light. During development, the unexposed emulsion is dissolved, and the oxide thus uncovered is removed by suitable etching techniques. Following cleaning processes, the slices are ready for a furnace treatment, in which boron is diffused into the silicon where the oxide has been removed. Thereafter, until the areas defined by the last of the series of masks have been treated, the alternation of photographic and furnace processes continues. In this way, all the circuit components are built up, and some of the interconnections, and electrical tests can be made before the slices pass on to the final process. The remaining interconnections and input and output connection points are formed by evaporating aluminium onto the surface. Afterwards, unwanted aluminium is removed by a final mask printing and chemical treatment. The slices are then complete. A slice is about 32 millimeters in diameter. It contains several hundred circuits, each about 1 millimeter square. Each circuit may contain 100 or even more components. In superimposing the patterns produced by the various masks, 6 to 15 in number, position is controlled to plus or minus 1 micron. These circuits are constructed either by bipolar or MOS technology. The colors seen on slices in certain lights are caused by oxide layers of varying thickness and resemble the colors seen on a soap bubble or a bloomed lens. In spite of great care and cleanliness throughout these operations, not every circuit is perfect. Faulty circuits must be detected before further work is done on them. The testing machines at Gem Mill are able to make a complex series of tests automatically at high speed. The slice is placed in position and correctly aligned by the operator. The machine then applies the prescribed sequence of tests to each circuit on the slice without further attention. Contact is made to the correct points by an array of up to 14 extremely fine probes. The target area for each probe may be as small as 25 microns in diameter. An inking device marks rejected circuits with a colored spot. The machine is a glutton for work and seems quite irritated when it comes to the end of a row. The probes remain in contact with each circuit for less than half a second. In that time, the whole sequence of test measurements is made and the verdict decided upon. The many devices on a silicon wafer are now ready to begin independent existences. A scribing machine, using a diamond-tipped tool, scores along the boundaries between the rows of devices. Once set to the correct pitch, it moves the required distance automatically between strokes. The slice being scribed in this case is a transistor slice, which has several thousand separate transistors on it. After scribing in two directions, the silicon wafer is easily broken along the scored lines, and the final production units appear for the first time, silicon dice. A slice can be manipulated with ease, but thousands of separate dice present a handling problem. To enable automatic machines to deal with them, they must be spread out, right side up. In the case of a transistor slice, this could mean several thousand nerve-wracking moves with tweezers. This device does the job in one move, and the only tension is in the rubber. Alloying machines fix the dice to headers. For this transistor type, these are small, inverted, gold-plated cans with lead-out wires already sealed in. Vacuum probes pick up the dice one at a time, and each is neatly placed on a preheated header and soundly scrubbed into union with it, the silicon forming an alloy with the gold where the two come together. The headers are collected in a magazine, which is transferred to the next machine. Electrical connections to the chips or dice are made by thermocompression ball bonds. Gold wire, 1/1000th of an inch or less in diameter, is used, and the connections to the base and emitter regions on the dice and to the lead wires are made by heat and pressure. A practiced operator can easily make 6 bonds in 6 seconds, a double bond being made to each external lead. Transistors of this type are encapsulated in Ferranti 2-stage RAM projection welding machines. These machines are totally enclosed, and the fully hermetic sealing is done in an atmosphere of filtered, dry, inert gas. But there are more ways of finishing off a transistor than by putting a hat on it. Recently, plastic encapsulated transistors have been introduced, the outcome of a new and highly automated production technique. Frames, blanked out of nickel and gold plated, provide the metal parts of the transistors in a flat layout, 128 side by side in each frame. Along the sides of the strip are location holes, used to feed the frame forward in steps through the machines. In the alloying process, the flag-shaped metal part which receives the chip is heated as it passes over a temperature-controlled platform, and the chip is accurately placed by a vacuum probe. The function of the operator is to move a good transistor chip into the pickup position each time, aided by cross wires in the microscope. The silicon dice used are first-quality planar transistor dice. The economies which enable these transistors to be sold at a low price are brought about entirely by the high degree of automation in the processing. The frames pass straight from the alloying to the bonding machine. Again, only one operator is required. Once the strip is fed in and engaged by the mechanism, the gold ball bonds to the base and emitter pads of the transistor are made automatically. As a bond is made, the wire parted off by a flame is left standing vertically, but is then bent so as to lie over the flattened end of the lead-out wire. A little farther on, a chisel-shaped tool bonds both wires simultaneously to their respective leads. The operator uses a microscope to position the bonds to a high degree of accuracy. The action is here slowed down to half the normal speed. The chisel is seen on the left. When 2 wires have been bonded to the dice and bent over, the strip moves on and the wire ends come under the chisel. A quick stroke bonds them securely to the external leads. This is one transistor as it leaves the bonding machine. For encapsulation, the frames are divided into subframes of 16 transistors, which are then loaded into a transfer molding machine. The epoxy resin used for encapsulation has been chosen with great care in the light of many years' experience in making resin-encapsulated diodes. The resin is first heated to about 150 degrees centigrade, which makes it as thin as water. Then it is forced into the mold under a pressure of 90 pounds to the square inch. This guarantees a free flow around the dice and lead wires, so that the structure becomes completely solid and mechanically very strong. In semiconductor manufacture, costly specialized machinery is the rule rather than the exception. But one of the most expensive operations of all is the testing of the finished product. This automatic, computerized transistor testing machine was designed, developed and produced in Gem Mill. Its purpose is to sort out a population of transistors into categories according to customer specifications. The only function performed by the operator is the loading of the transistors into the test heads. Round the table are 6 test positions, which the transistor encounters in turn. A total of 125 tests can be made, each taking about 100 milliseconds. As a transistor leaves each test position, the results of the tests performed are stored in the computer's memory, and a visual indication of the results appears on the bank of lights. As the transistors progress through the test positions, the code of lights progresses down the column, and new results are added row by row. Any combination of the 125 possible test decisions can be programmed into the machine in a few minutes. To satisfy a particular delivery requirement, the program can be arranged to give preference to certain combinations and to inhibit other groups of decisions. When the test sequence is finished, the transistors are ejected onto a moving magnetic belt, where each one is intercepted by a hydraulically operated arm and diverted into the bin corresponding to the desired specification. Returning to integrated circuits. When the slices have been scribed, the circuits are separated and alloyed to headers. Bonding of some types is done on these machines, which are more complex than the transistor bonding machines in that the header can be rotated as well as moved in the X and Y directions. A sheaf of diagrams beside each operator shows the connections required for the various circuits. Precise control of movement enables the operator to make good thermal bonds to connection points as small as 25 microns across. As with transistors, integrated circuits are available in epoxy resin encapsulations. The continuous production system used for some of these is similar to that employed for plastic transistors. The operator brings a chip into the pickup position, the machine alloys it to the small platform in the middle of a frame, and so on to the end of the strip. Each assembly on the strip is about an inch square. When the frames reach the bonding machine, the contact points on the chips are connected to the appropriate leads with gold wire and thermocompression bonds. Each connecting wire is only about 2 millimeters long. In this close-up, the characteristic nail head shape of ball bonds is clearly seen. The wires are fine enough to be invisible to the unaided eye. A transfer molding machine completes encapsulation of the devices in 3 minutes or so. Once enclosed in solid epoxy resin, microcircuits are finally free from the great hazard which has been with them all through their manufacture, dust. Only air filtered to half a micron has ever come in contact with them. The water supplies used are similarly filtered and deionized. Special clothing is worn by workers and visitors too. But dust particles down to the size of bacteria can turn good microcircuits into failures. After encapsulation, the leads are separated by punching out the ties. The gold plating is stripped off and the leads tin plated. The square frame is removed and a final squeeze bends the leads over, ready for inserting into a printed circuit board. When the assembly processes are completed, integrated circuits enter a phase of exhaustive electrical testing. In aging racks, they are run for up to 48 hours under conditions of temperature and dissipation much more severe than any they are likely to encounter in use. The plug-in modules used in these racks allow hundreds of circuits of different types to be processed at the same time. Before and after aging, every circuit is tested electrically for leakage currents, operating times, and other characteristics. For low-volume production runs, testing is done on modular equipment which can be programmed to measure any parameter of any circuit under all possible conditions of input and output. Fully computerized test gear is used for devices in large volume production. The high operating speed of modern integrated circuits, which has made possible extremely fast and compact computers, has also made necessary a whole new philosophy of testing and evaluation. In the rarefied atmosphere of measurement which reigns here, a microsecond is a very long time indeed, and periods of time in which light will travel only a foot are critically examined. For some applications, silicon integrated circuits are combined with thin film circuits, as in the multilin range of hybrid units made by Ferranti at Bracknell. Thin film resistor conductor and capacitor patterns are selectively etched in metal films on glass. The silicon chips are mounted on ceramic substrates to ensure good heat dissipation. The assembly is interconnected using thermocompression bonded gold wire, giving a unit of extremely high package density and great reliability. 200 conventional components can be replaced by one multilin unit. Another micropacking process has been put into full production by Hawker Siddeley Dynamics. Silicon chips made at Gem Mill are mounted on ceramic wafers 8 mm square, with connections to vacuum-deposited conductive tracks leading to edge terminations. Up to 14 of these can be assembled in stack form. The edge terminations are wired up using a computer-controlled electron beam welding machine. The finished assembly in its hermetically sealed welded can is only 2 centimeters high and 1 centimeter square. Another way of marrying silicon chips and thin film elements is practiced at the Wythenshawe laboratories. Through his microscope, this operator sees 2 images superimposed, one of a specially prepared thin film circuit, which is face up, the other of a silicon chip suspended above this, face down. The thin film element is moved by delicate controls until the image of a prepared area on its surface coincides exactly with the image of the chip. The chip is brought down into contact with the glass substrate, and heat and gentle pressure bond corresponding contact points together without the use of connecting wires. Several chips may be used in each flip-chip hybrid circuit. A view through the reverse side shows the chips and connections. Following years of heavy financial investment, building up technical knowledge, and creating much unique precision machinery, integrated circuit production at Gem Mill began to gather momentum in 1965 and has continued to grow in range and quantity. Now Gem Mill has 1,500 employees, and a new factory to take 1,000 is in operation at Barrow-in-Furness. The Barrow factory is an assembly unit only, but one that uses British dice, fully processed at Gem Mill. With the demand for silicon circuits still multiplying, Barrow is not likely to be the last such extension. Many of those thousands of integrated circuits will go into computers. Computer technology and silicon sophistication grew up side by side in the Ferranti organization, and radically new computer designs have been the result. The Argus 400 was one of the first of the new breed, a fast, supremely reliable general-purpose computer using over 1,000 Micronor 2 circuits in its central processor. This half-cubic foot of streamlined computing power represents, more or less, the present state of the art of using the integrated circuit in production equipment. What lies ahead? Circuits will become more complex, and novel systems of construction will be devised, demanding closer cooperation between equipment maker and semiconductor manufacturer. A country whose industry can provide this cooperation will have a future in electronics. A country which rejects it will be an electronic nonentity, a mere assembly line, and a sitting target for exploitation by others.